Welcome to this next session on UV-Vis molecular absorption spectroscopy, where we will be talking about UV-Vis measurements and talking through some worked examples, some processes, and some useful techniques while conducting these measurements, and just some all-around tips on how to make use of UV-Vis absorption measurements in your instrumental analytical chemistry. So quantitative analysis is usually the major application of UV-Vis absorption spectroscopy. Typically, what we're looking at is the best way to kind of measure these samples. How can we try and get a concentration usually, or a ratio of concentrations between our components or our analytes in solution. So UV-Vis is usually, because of the broad spectra involved, usually they're complicated by vibrational and rotational lines, as well as our electronic transitions, which is really the effect that we're making use of. UV-Vis is an important tool for quantitative analysis. Qualitative, it's a little bit harder. It is possible with things like gas phase molecules, or with molecules that are in a very non-polar media. So it can be applied widely to both organic and inorganic systems. Basically, so long as it's got some sort of an energy transition, which is in the UV or visible region, it can be measured, which is pretty much everything. But it's more useful for some things versus others because of its limitation to only quantitative analysis. It's sensitive to low concentrations. In fact, as we learned before, there's such things as limit of quantitation, a limit of detection. So long as it's above that limit of quantitation and it's still in the linear range of the Beer-Lambert law, we really can make use of low concentrations. Oftentimes you have to dilute your sample in order to get it low enough. It has moderate to high selectivity. It's got good accuracy, usually less than 3% uncertainties. So it means it's going to have good reliability. It's easy and convenient data acquisition. You can do it very quickly. It's really got a high throughput, so long as you prepare your samples in advance. Moderate to high selectivity. Again, if you choose your wavelengths correctly and you choose your media correctly, you're going to really only be measuring the analyte that you want to measure. So some key terms with regards to these. So typically you're going to hear these things bandied around or said whenever we are talking about these processes or these techniques. So you're going to have radiant power, which is P and P0. An alternative name is radiant intensity, I or I0. So these are the lights which are incident and after the sample. So this is usually what we're measuring, because remember, we're putting a broad spectrum of wavelengths across the sample. And then what we're doing is we're measuring how much of the light is absorbed by our sample. Absorbance A, or optical density D. Optical density is a very traditional word to use. If you look up older literature, which you probably will often do whenever you're doing these measurements, because a lot of the data for a lot of molecules and things like that were published decades ago. And they used the term optical density instead of absorbance back then. Absorbance is more of a modern word. I mean, it existed around that time, but optical density was really more what they were using. Transmittance T, sometimes called transmission. These are used interchangeably. They both have the same letter, transmittance and transmission. Path length B, sometimes called L for length or D for distance. Any of them are okay. So long as you know what you're talking about and you don't get confused, you can use whatever letter you want. Absorptivity A, sometimes called the extinction coefficient K. It's often, though, reported as the molar absorptivity. So it's the absorptivity per mole of a particular substance, or known as the molar extinction coefficient, both of which have the letter epsilon. These are just like how much, or like what it, like it's the factor which is molecule or species dependent, which we're going to see used. So it's kind of like a correction factor for a measurement based on the particular behavior of our analyte. So we do have some assumptions in the absorption law that our incident radiation is monochromatic, so we're measuring the sample only at one wavelength. So typically what happens is you have a monochromator which selects the wavelengths from our tungsten filament lamps and our deuterium lamps. So what's happening there is that the monochromator picks a very narrow range of wavelengths to irradiate the sample with, so that the light is monochromatic of one wavelength. Then the absorbing species should act independently of each other. That means they shouldn't interact with each other, form a charge transfer complex, things like that, unless that is what we happen to be measuring, in which case that's also okay. Incident radiation consists of parallel rays perpendicular to the surface of the absorbing medium. So incident radiation consists of parallel rays. So that's what the collimator is for, so that all of the rays are passing through the sample and so they can be picked up at the other side in the same position. So this means that they're going to be perpendicular to the surface of the absorbing medium, which means that they're going to come in at right angles, so that the wall of the cuvette and the beam of light coming in can be described by being 90 degrees rotated from each other. The path length traversed is uniform over the cross section of the beam. So what does that mean? It means that if at any point in the beam, if we have a 1 centimeter cuvette, the walls are straight up and down. They don't like curve in or something like that. The path length for the whole of the beam that passes through the sample. So the beam is usually quite small and tightly focused, but there should be no deviations in the path length. The path length should, if it's a 1 centimeter path length cell, it should always be 1 centimeter path length cell. The walls should be perfectly flat and straight up and down. The absorbing medium should be homogeneous and does not scatter radiation. So there shouldn't be any particles inside of our sample as to the best of our knowledge. Sometimes a little bit of dust gets in there. Really, you want to make sure that there is no dust, but sometimes it happens. Because the problem with the dust is the dust particles can scatter radiation. You want to make sure that you've avoided that as much as possible. So usually you want to work in a positive atmosphere room. Incident flux is not large enough to cause saturation effects. So lasers can usually cause these effects. So what does this mean? It means like that we're not saturating the sample with energy from our electromagnetic radiation. We shouldn't be overwhelming it with too much energy, which could cause destruction of our material, which would affect the final result of our absorption measurements. We should also not have a lot of change in the energy, which is incident on our sample. So there should be like a consistency of the energy, which is transferred from the light source to the sample itself. So again, remember, we talked about this way back at the start. Absorbance is additive. So if we have multiple species absorbing at the same wavelength, the absorbance that we get out of our spectrometer is going to be the sum of the individual species which are absorbing at that wavelength. So absorbance of the total absorbance, which is what we'll observe using our instrument, is going to be equal to the sum of all of the individual absorbances. So A1 plus A2, etc. And so that's going to be equal to epsilon BC1 plus epsilon 2 BC2. So that's for species 1, species 2. They have their individual molar absorptivities, they have their individual concentrations, but their path lengths remain the same because they're contained within the same sample holder, the same cuvette or whatever it happens to be. So for a 2 absorbing species system, we can describe it like so. So the absorbance at our first wavelength is going to be equal to the epsilon 1 of our species at wavelength number 1 times B, which is the path length, times C1, which is the concentration of species 1. And to that, what we're going to do is we're going to add the absorbance described by the Beer-Lambert law of species 2, where we have epsilon 2 at wavelength number 1, which is what we're measuring at, remember, times the path length B times the concentration of species 2 in our solution in our system. Then we can do the same thing at a different wavelength. We can get the absorbance at wavelength number 2. Then we have epsilon 1 at wavelength 2 times the path length B times the concentration C1 plus epsilon 2 times epsilon 2 at the wavelength 2 times the path length times the concentration of the second species. So hopefully you can see where we're going here. We're doing some algebra. So the molar absorptivities of X and Y were measured with pure samples of each, and we can use these values here. So we have the wavelength, two wavelengths. We have the epsilon for species 1 and species 2 at the two different wavelengths. So here's the molar absorptivity of this one for species Y, which could be species 2 up here. And then here's the molar absorptivity at 272 nanometers for species X, which could be epsilon 1 and species 1 up here in our equations. So now we're going to try and solve these equations to try and determine the values of our system. So we have this table of data. We have a process by which we can calculate things. So we're asked a mixture of compounds X and Y in a 1 centimeter cell had absorbance of 0.957 at 272 nanometers and 0.559 at 327 nanometers. And we're asked to find the concentration of X and Y in our mixture. So here's our table. So we have lambda 272 over 327. X is epsilon values here. Y are epsilon values here. So we have absorbance at wavelength 1, which is 272 nanometers, and we have absorbance at wavelength 2, which is 0.559. So we'll add those values in there. We have our epsilon values here, so we'll add those in as well. So we'll be able to solve these equations by putting them in terms of only one of the concentrations. So basically it becomes 0.957 as the absorbance at wavelength 1, which was 272 nanometers, is equal to 16,400, which is the epsilon 1 of our species X, or species number 1 at wavelength number 1. We've omitted the path length since it's 1 centimeter. It just multiply this by 1, you get the same value. Then we have here the molar absorptivity of species Y at 272 nanometers times the concentration of Y. And then the second equation, so that's going to be at wavelength number 2, which is 327 nanometers. So the absorbance at wavelength number 2, 327 nanometers, is 0.559. And that's going to be equal to the epsilon 1 or epsilon of X at wavelength number 2. So that's going to be 3,990 at wavelength of 327 nanometers for species X, or species number 1, plus the epsilon for the species Y, which is our second species, at their second wavelength, which is going to be 327 nanometers times the concentration of Y. So now we have two equations of a similar form, both in terms of X and Y. So we have to rearrange these to get it in terms of either X or Y, and then we can substitute that into the other and find the value for either X or Y. And then using one of the equations, we can find the value for the other. So by doing that, we get a final value of X is equal to 4.43 times 10 to the minus 5 moles per liter, and then Y is equal to 5.95 times 10 to the minus 5 moles per liter. So what we would do is if we wanted to have this equation in terms of X, we'd subtract both from both sides 6,440 times Y, and then we would divide through by 3,990. We would have X on its own. And so X could be substituted into this. So this equation would be totally in terms of Y, and then we could solve it for Y, and then we get the value for Y, and then we substitute the value for Y into one of the equations, and then we can get the value for X. Path length. So if a sample for spectrophotometric analysis is placed in a 10 centimeter cell, the absorbance will be 10 times greater than the absorbance in a 1 centimeter cell because it is linearly dependent on path length. Remember, our Beer-Lambert law is A is equal to epsilon BC, where B is the path length. If B is 1, you multiply the whole thing by 1. If B is 10, you multiply the whole thing by 10. So will the absorbance of the reagent blank solution be increased by a factor of 10? So here we have A is equal to epsilon BC, where epsilon BC is our path length and A is our absorbance. And so increasing B X times will also increase A X times. So yes, it will. Dilution corrections. So oftentimes we're dealing with solutions which are too concentrated for the Beer-Lambert law. And so we have to dissolve it in something. I have to dilute it so that it would be within the linear range of the spectrometer, the linear range of the Beer-Lambert law. And so the absorbance measured after adding 125 microliters, which is equal to 0.125 milliliters of ferric nitriloacetate to 2 milliliters of aptotransferrin, which is a clear solution, was 0.260 from the complex formed. And we're asked to calculate the corrected absorbance. So what is the corrected absorbance? Remember, we've diluted our solution here so that we could get an absorbance of less than 1. So that would be usually within the linear range. Usually your absorbance, you'd want it to be less than 1. At the very most, it should definitely be less than 2. Absorbances greater than 1 are usually suspect. So you want the absorbance to be somewhere between, I don't know, like 100 and 0.1 and like 0.8 or 9. Calculate the corrected absorbance. So the corrected absorbance is going to be equal to the total volume divided by the initial volume times the observed absorbance. So remember, we've diluted, so this is our dilution factor. So the total volume divided by the initial volume is going to be our dilution factor times the observed absorbance. So it's going to be 2,125 over 2,000 times 0.260 is going to be equal to 0.276. So that's going to be our corrected absorbance. So what we have here is the total volume is the aptotransferrin plus the ferric nitriloacetate. So that's 2,125 microliters over 2,000 microliters, which is 2 milliliters, times the absorbance that we measured is equal to 0.276 for the corrected absorbance. Okay, so what are the effects of stray light? Well, typically it means that we see a reduction in the observed absorbance. So PS is the power of the stray light over P0, which is our regular radiation. So we see here the percentage of stray light. So in an ideal case, we have 0% stray light. So what is stray light? Stray light is light inside of the spectrometer, which didn't come from our light source or didn't come from the sample. And so it has the effect of reducing the observed absorbance. So if we look at here, so PS over P0 times 100%. So the fraction of the total, which is the stray light, and how it increases. So at like 0%, that's a linear relationship. We have a pure linear Beer-Lambert situation. As we increase, you can see even here that there's a significant deviation, especially at high concentrations. And up to 5%, we can see that anything above 2.5 times 10 to the 3 concentration, times 10 to the minus 3 concentration. Remember, this is concentration times 1,000. So 2.5 times 10 to the minus 3 is going to be the maximum concentration we can measure if we have 5% stray light within our spectrometer. Whereas we can go to higher concentrations and get correct absorbances if we have less stray light. So this is why stray light is so important to eliminate. So the transmission is equal to P plus PS over P0 plus PS, where the PS is the stray light. And so A, remember, is equal to minus log to the T. So A can be equal to minus log of this term here, which takes into account the stray light. And then, so P is the power after, P0 is the incident power, and then plus the stray light. And so A is equal to ABC is equal to KC, where K is this constant. So calculation of concentration. So a compound with molecular mass of 292.16 was dissolved in a 5 milliliter flask. A 1 milliliter aliquot was taken and placed in a 10 milliliter volumetric flask and diluted to the mark. The absorbance at 340 nanometers was 0.427 in a 1.000 centimeter cuvette. The molar absorptivity at 340 nanometers is going to be epsilon is equal to 6,130 per mole per centimeter. Calculate the concentration of the compound in the cuvette. So we can calculate it using the information that's in the question. And so we can find the concentration in the cuvette because we have the absorbance and we have the path length. So the path length is going to be 1 centimeter. The absorbance is given here, and the molar absorptivity is this. So it's going to be the Beer-Lambert law, which is A is equal to epsilon BC, and then we fill those in. We rearrange. We have the absorbance here. We have the wavelength that it happens at, the epsilon here, and we have the 1 centimeter cuvette. We rearrange this, and we get C has a value of 6.97 times 10 to the minus 5. Okay, let's try that again. So calculation of concentration. So a compound with molecular mass 292.16 grams per mole was dissolved in a 5.00 milliliter flask. A 1.00 milliliter aliquot was taken and placed in a 10 milliliter volumetric flask and diluted to the mark. The absorbance at 340 nanometers was 0.427 in a 1.000 centimeter cuvette. The molar absorptivity at 340 nanometers is epsilon is equal to 600 or 6,130 per mole per centimeter. So calculate the concentration of the compound in the cuvette. So here we'll just use the Beer-Lambert law. Absorbance is equal to epsilon BC, since we have everything we really need. We have the molar absorptivity at a certain wavelength. We have the absorbance at that wavelength. We have the path length. And so we're able to just rearrange the equation so that we have it in terms of concentration is equal to absorbance over epsilon B, which we just fill in the values here. So 0.427 over 6,130 times 1 centimeter gives us a concentration then of 6.97 times 10 to the minus 5 moles per liter. Now, since we did dilute this by a factor of 10, we're asked, what is the concentration of the compound in a 5 milliliter flask? So the original concentration, what is the original concentration after the dilution? So that's just going to be multiplied by our dilution factor. So the concentration is going to be multiplied by the volume, the final volume over the initial volume. So the final volume was 10 milliliters. The initial volume was 1. So it will be equal to 6.97 times 10 to the minus 5 moles per liter times 10 over 1 is going to be equal to 6.97 times 10 to the minus 4 moles per liter as the concentration in the 5 milliliter flask. So it's just our dilution factor. So how many milligrams of compound then were used to make the 5 milliliter solution? So we have the concentration here, so we need to know the number of moles. So the number of moles is going to be equal to the volume times concentration. So the volume was 5 milliliters in the 5 milliliter flask times the concentration, which is this, which will give us this number of moles, 0.003485 moles. We don't round up until the end. And then, so we have 0.003485 moles times the molar mass, which was 292.16 grams per mole, which will give us the number of grams in that as 1.017 times 10 to the minus 3, which is grams. Then multiply that by 1,000, we would get 1.017 milligrams. Okay, so that's kind of how we would use it to determine concentrations, how we would use dilution factors, and how we would calculate back. So the scope of quantitative use. So far we've only been dealing with things that actually absorb in the UV-Vis region of the spectrum, but that's kind of the normal stuff. Like any chromophore can be theoretically spectroscopically determined. But can we measure non-absorbing species like certain metal ions which don't absorb in the UV or Vis, certain other species which have complicated relationships with their internal bonding and things like that? Like, can we measure non-absorbing species? The answer is yes, yes we can. How do we do that though? Like, how do you measure something if it's not going to measure? How do you measure something in the UV visible if it doesn't actually absorb in the UV Vis? Well, you coordinate it with something that will, and that something that will should hopefully move the absorbance into the UV Vis region. So how do we detect a non-absorbing species? If the non-absorbing species will react to form an absorbing species, for example, ethanol, which oxidizes chromium 6+ to chromium 3+, that is an absorbing species. And so we have the ability to, so chromium 6+ does not absorb, chromium 3+ does. So we oxidize the chromium. Inorganic species may be complexed with things like thiocyanate. So we can use inorganic anions to coordinate here, and that can create a charge transfer complex, which can in fact lead to absorbance in the UV vis. Treating titanium, vanadium, or chromium with hydrogen peroxide, iodide with for bismuth, palladium, and tellurium. Organic reagents can be used to complex our metal ions. So for example, if we have copper, we might want to use diethyl dithiocarbamate. So here is something which could coordinate to copper. Then we've got the 110 phenanthroline, the iron. So that could, this is phenanthroline here, and that should be with iron. And then we have, of course, our palladium or our nickel. So that can coordinate with dimethylglycine. So this is something that coordinates to palladium or nickel. So really what I want you to take away from this is that for non-absorbing species, there's usually like three major, like it's usually metal ions. Okay. Usually metal ions that are non-absorbing, usually because the transitions are too high in energy. So they're like way down in like the microwaves or the X-rays or something like that, high energy. So what we do is we do something to move their transitions into the visible. Remember, like we're not really too concerned. Like usually whenever we're doing these measurements, we want to know how much of something there is. We're not really concerned about changing its species. So for example, if we oxidize it, which is one of our routes, from chromium 6 to chromium 3+, we have the same amount of chromium at the end. It's in a different form, but the concentration will still be the same. So for example, our three major methods usually are through oxidation, through complexation with inorganic species, or through complexation with organic species. Those are our three major routes to doing this. Okay, measuring procedure for a UV vis absorption measurement. We want to measure at the absorption maximum. So this is the largest change with concentration and adheres best to Beer's law. So we usually do a broad sort of like measurement of the spectrum and sort of see which area or which wavelength is the lambda max. And then we'll do all of our measurements thereafter at that lambda max. We want to control the conditions. So we want to make sure we have the same pH in all of our solutions. We conduct it at the same temperature. The room humidity doesn't fluctuate too much, things like that. So usually we have a temperature and humidity controlled room. Then we want to establish the relationship between absorbance and concentration. So we have to get some sort of a calibration chart. We've talked about linear regression methods before and the different calibration methods can be used. So we want to bracket the unknown concentrations. That means we usually want to have 2 or 3 data points either side of the concentration that we're interested in. We want to have more than 3 external standards, and the external standards should closely follow the unknown sample composition. So like this, the external standards are like the concentration, the known concentrations that we use to create our linear regression or our calibration plot. If not possible, then we'll use the standard addition method. This is where we add aliquots to our sample that we've obtained. Usually this is for environmental samples, since environmental samples are typically very complex. And then of course we measure the unknown sample. So the standard addition method, we've talked about this before back in module 1. So add 1 or more, preferably 5 increments of a standard solution of analyte in the same solvent. So for example, say we have river water and we want to know how much copper or iron there is there. So say it's copper, and we would make up a solution of copper in water, and then we would add that to our analytical sample that we have obtained from the environment. And then we would take an account of how much of that sample we're adding, the volume, the standard volume added, and then we would look at the absorbance and how that changes. And then by extrapolating back, we can find the value for the original solution. Photometric titrations. So we measure the absorbance as we add titrant. So basically, we have our titration happening inside of a spectrometer, and we slowly add certain volumes, and then we can use that to determine the concentration. So measure the absorbance as we add the titrant. Then the absorbing system must obey Beer's law, and so the volume changes must be corrected for so. So like, for example, the absorbance is equal to the absorbance times the volume plus the added volume all over the initial volume. So this is just our dilution factor effectively. So it's the final volume over the initial volume. And then low concentrations can be titrated here. So we can see here how the absorbance changes with the volume of titrant. So for example, in this case, what's happening here is that we're changing the system, and the absorbance is decreasing until we reach this point where we have our complete reactions. This is kind of our end point, and then here is beyond our end point. Kinetic methods can also be done, so we can measure the rate of formation or consumption of the absorbing species at a specific wavelength. So what we can do is we can set up our reaction inside of the spectrophotometer, and then we can inject some of our sample. Some spectrophotometers are set up already so that they can be done using kinetic methods. So they have like a little holder then for the syringe or whatever to slowly add our sunlight, or you can add it using a syringe very quickly and start the measurement, and then measuring. Usually it's only possible to do this at one wavelength at a time. So usually you want to be doing this at the lambda max of your original sample, or at the thing that you're trying to measure the formation of. And so then you have time across here and the absorbance here. So this is presumably the formation of some chromophore. So you can see here, we measure it at fractions of a second, and then we can fit this to our curve like so. So we can see this is a very fast reaction. So concentration determination can be done using external standards. Then if we have two, we can determine binding constants through a method of continuous variation. So continuous variation method allows determination of binding constants. The mole ratio of two components is varied, but the total moles remain same. So for example, say we have 1 mole total in the solution, we could measure at 0.5 mole to 0.5 mole, 0.25 to 0.75, and so on, things like that, 0.33 to 0.66, that sort of thing. And so the curvature of the lines is due to the incompleteness of the reaction. And so this is an equilibration reaction, an equilibrium reaction. So the continuous variation method allows us to determine the concentration between two species. So I remember I showed you this one in the previous session where we had a charge transfer complex formed between two colorless solutions. One was an ionic liquid, the other was an organic liquid called methyl naphthalene. We mixed those together and we got a colored sample, kind of yellow colored. It came out orange in the photograph, but basically it's kind of a yellow color. And then this continuous variation method allowed us to determine what the optimal concentrations were for the formation of the complex. So the Beer-Lambert law, a worked example, so just as revision. So given the Beer-Lambert law as absorbance is equal to epsilon BC, what is the molar absorptivity of a solution with absorbance of 0.5, path length 1 centimeter, and concentration 1 times 10 to the minus 3 moles per liter? So we fill in our values. So absorbance is equal to epsilon BC, where epsilon is equal to 1 centimeters times the concentration here, which means that we would eventually have just an absorbance of, the is equal to 0.5, which is our absorbance. So then we rearrange this to be in terms of epsilon. So we find that epsilon is equal to 0.5 divided by 1 times 10 to the minus 3. Remember, 1 centimeter kind of just cancels out. And so then we have equal to 500 liters per mole per centimeter as our epsilon. Okay, so then let's look at an acidic indicator example. So this is a two-step indicator where the absorbance is recorded for the indicator at two different wavelengths for both the weak acid and its conjugate base. So here's our equilibrium with Ka is equal to 1.42 times 10 to the minus 5. So that's our equilibrium. So solutions prepared in 0.1 molar sodium hydroxide and hydrochloric acid. So we have the absorbance versus total indicator concentration. So we have a nonlinear response at 430 nanometers and 570 nanometers, but both obey Beer's law at those wavelengths. So the concentration total is going to be equal to the concentration of the undissociated acid and the conjugate base. And so we're told the total concentration is 2 times 10 to the minus 5 moles per liter. So we're asked, what are the absorbances in a 1 centimeter cell at both of these wavelengths? So since Ka is equal to this, and then this is our reaction quotient for that, or our equilibrium expression for that reaction equilibrium here, then the concentration of H plus is going to be equal to the concentration of indicator or of the conjugate base of the indicator. And then that means that we're going to have the sum of these two is equal to the total concentration. So then we can put that into our equation here to get it all in terms of the indicator. And so indicator concentration, the conjugate base concentration, I mean, which is going to be equal to our Ka value here. And so then we can rearrange and solve using the quadratic equation. The x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Where we rearrange this to get the quadratic equation. We can find then that the indicator concentration is this, and the weak acid concentration is this. So then we know that the absorbance, the total absorbance, is equal to the sum of all of the individual absorbances. And so we can, since we know the concentration of the two species, we know the epsilon values, we can just, and we know the path length in a 1 centimeter cell, we can just find the absorbance pretty easily as this. So absorbance is equal to the epsilon of the conjugate base times the path length times the concentration of the conjugate base plus the epsilon of the weak acid undissociated times the concentration or times the path length times the concentration of the undissociated acid. And so we fill in our values at epsilon, either one. It doesn't really matter which one we calculate it at, but basically do it at one of them. And then we fill in the values from the table and from our question and from what we've calculated. We get the absorbance at one of the wavelengths as 0.236. Then it's your job to calculate it at epsilon is equal to, or at 570 nanometers. So that's your work. And then just pause the video, have a calculation, see if you can come up with the correct answer. It shouldn't be too hard. It's basically just changing the values for epsilon in this equation. And then you should come up with a value of this for the absorbance at 570 nanometers. And that is us for today's session. Thank you for watching.